In November 2022, a chatbot called ChatGPT broke the internet. Within 5 days, it had 1 million users. Within 2 months, 100 million. It sparked conversations in boardrooms, classrooms, and living rooms around the world. But ChatGPT didn't appear out of nowhere. It was the culmination of years of research, experimentation, and incremental breakthroughs by a company called OpenAI. Today, we're tracing that journey from the modest beginnings of GPT-1 in 2018 to the global phenomenon of what we now know as ChatGPT. We'll explore the technology behind these models, look at real-world applications, and separate fact from fiction when it comes to what these systems can actually do. This is the rise of OpenAI, from GPT-1 to ChatGPT. Let's dive in. Our story begins in June 2018, when OpenAI released a research paper introducing GPT-1, the generative pre-trained transformer. At the time, it had 117 million parameters. Now, that might sound like a lot, but by today's standards, it's tiny. What made GPT-1 significant wasn't its size, but its approach. The researchers demonstrated that you could take a neural network, pre-train it on massive amounts of text from the internet, and then fine-tune it for specific tasks like answering questions or classifying text. This two-step process, unsupervised pre-training followed by supervised fine-tuning, became the blueprint for everything that followed. Less than a year later, OpenAI released GPT-2 with 1.5 billion parameters, more than 10 times larger than its predecessor. This model could generate remarkably coherent paragraphs of text. It could write stories, answer questions, and even translate languages, all without being explicitly trained for those tasks. But GPT-2 made headlines for another reason. OpenAI initially refused to release the full model, citing concerns about potential misuse. They worried it could be used to generate fake news, spam, or other harmful content at scale. This decision sparked a debate about research transparency and AI safety that continues today. Eventually, they did release the full model after conducting safety research and seeing that other organizations were creating similar systems. Then came GPT-3 in June 2020, and this was a genuine leap forward. With 175 billion parameters, it was more than 100 times larger than GPT-2. But size wasn't the only story. GPT-3 demonstrated something remarkable. With the right prompting, it could perform tasks it had never been explicitly trained to do. You could show it a few examples of a task, like translating English to French or writing product descriptions, and it would continue the pattern. This capability, called few-shot learning, suggested that as these models got larger, they developed more general-purpose abilities. OpenAI released GPT-3 through an API, allowing developers to build applications on top of it. Suddenly, startups were using it to write marketing copy, generate code, create customer service chatbots, and more. The commercial potential was becoming clear. But there was a problem. These models were powerful, but they weren't always helpful or safe. They might generate offensive content, make things up, or give unhelpful responses. OpenAI needed a way to align these models with human values and preferences. Enter reinforcement learning from human feedback, or RLHF. Here's how it works. First, you collect examples of model outputs and have humans rank them. Which response is better? Then, you train a reward model to predict human preferences. Finally, you use reinforcement learning to fine-tune the language model to maximize that reward. In simple terms, you're teaching the model to generate responses that humans find more helpful, harmless, and honest. This technique had been explored in research, but OpenAI applied it systematically to create InstructGPT in early 2022, a version of GPT-3 that was much better at following instructions. Which brings us to November 30th, 2022. OpenAI took the lessons from InstructGPT, applied them to a new model, and released it with a simple chat interface that anyone could use for free. They called it ChatGPT. What made ChatGPT special wasn't that it was the most powerful language model ever created. It wasn't. What made it special was that it was useful, accessible, and surprisingly good at understanding what people actually wanted. It could explain complex topics, help with homework, write code, brainstorm ideas, and have remarkably natural conversations. Within days, it had captured the public imagination in a way no AI system had before. So how do these large language models actually work? Let's break down the key concepts. First, understand that these models don't read text the way we do. They work with tokens, small chunks of text that could be whole words, parts of words, or even individual characters. The word understanding might be split into tokens like under, stand, and ing. The model learns statistical patterns about which tokens tend to follow which other tokens based on the training data. When you type a message to ChatGPT, your text is converted into tokens, processed through billions of mathematical operations, and then the model predicts what tokens should come next, one at a time. It's doing extremely sophisticated pattern matching at an enormous scale. During pre-training, these models are exposed to vast amounts of text, books, websites, articles, code repositories, and more. The training objective is simple: predict the next token. But to do this well across countless different contexts, the model has to develop internal representations of grammar, facts, reasoning patterns, and even some common sense about how the world works. This is unsupervised learning. No human is labeling examples as right or wrong. The model is simply learning the statistical structure of human language by processing billions of examples. After pre-training, the model can be fine-tuned for specific tasks. This involves training it on a smaller, curated dataset with explicit supervision. For example, you might fine-tune a model on examples of good customer service conversations or on medical question and answer pairs. This helps the model perform better in particular domains. As we mentioned earlier, reinforcement learning from human feedback is the final step that makes models like ChatGPT actually useful. It's not enough for a model to be able to generate fluent text. It needs to be helpful, it needs to decline inappropriate requests, and it needs to admit when it doesn't know something, rather than making up plausible-sounding nonsense. RLHF is computationally expensive and requires significant human effort, but it's what transforms a raw language model into a conversational assistant. So what are people actually using these models for? The applications are remarkably diverse: content creation for marketing and social media, customer support and chatbots, coding assistance and debugging, research and summarization, education and tutoring, brainstorming and creative writing, data analysis and extraction, and language translation. The key insight is that these models are general-purpose tools. Unlike previous AI systems that were built for one specific task, large language models can be adapted to almost any task that involves language. Let's look at 3 concrete examples of how organizations are using this technology. A mid-sized e-commerce company was drowning in customer support tickets. They had a team of 20 support agents handling everything from order tracking to product questions to return requests. Response times were averaging 24 hours, and customer satisfaction was suffering. They implemented a system using GPT-3 that could automatically respond to common inquiries. Questions like, "Where is my order?" or "What's your return policy?" The model was fine-tuned on thousands of historical support tickets and responses. The result? About 60% of incoming tickets could be fully resolved by the AI system without human intervention. For the remaining 40%, the system would draft an initial response that a human agent could review and edit. Average response time dropped from 24 hours to under 2 hours. The support team didn't shrink. Instead, agents spent more time on complex issues that required empathy and creative problem-solving. Conceptually, this works because customer support involves recognizing patterns in questions and matching them to appropriate responses, exactly what large language models excel at. A digital marketing agency was struggling to keep up with client demand for blog posts, social media content, and email campaigns. They had talented writers, but the volume of content needed was overwhelming. They started using GPT-3 as a first draft generator. A writer would provide a brief, the topic, key points, target audience, and tone, and the model would generate an initial draft. The writer would then revise, fact-check, add creative touches, and ensure the content aligned with the client's brand voice. This didn't replace the writers, it augmented them. What used to take 2 hours to write from scratch might now take 45 minutes to refine from a strong first draft. The agency could take on more clients, and writers spent more time on the creative and strategic aspects of their work rather than staring at blank pages. The key lesson here is that these tools are most effective as collaborators, not replacements. A startup was building a mobile app but had a limited engineering budget. Their founders had some technical background but weren't expert programmers. They used GPT-3-powered tools to help write code, debug errors, and understand documentation. When they got stuck on a problem, say how to implement user authentication, they could describe what they were trying to do in plain English and get working code examples. When they encountered an error message they didn't understand, they could paste it in and get an explanation along with potential solutions. This didn't make them expert developers overnight, but it lowered the barrier to entry significantly. Tasks that might have required hiring a consultant or spending hours searching through Stack Overflow could often be solved in minutes. Conceptually, this works because programming languages are just specialized forms of language with rigid rules, and these models have been trained on billions of lines of code from open-source repositories. Now let's address some common misconceptions about these systems. When ChatGPT writes a coherent essay about photosynthesis, it's tempting to think it understands biology. But that's not quite right. These models are sophisticated pattern-matching systems. They've learned statistical correlations between words and concepts from their training data, but they don't have mental models of the world the way humans do. Consider this. If you ask ChatGPT about a news event that happened yesterday, it can't access that information because it wasn't in the training data. If you describe a completely fictional scenario, it will respond as if it's plausible because it's pattern matching to similar structures in its training. A human would know the difference. This doesn't mean these models aren't useful. They absolutely are. But we need to understand them as incredibly sophisticated statistical tools, not as thinking entities. Large language models can confidently state completely false information. Why? Because they're trained to generate plausible-sounding text, and sometimes plausible doesn't mean accurate. This phenomenon is often called hallucination. The model generates facts, citations, or details that sound real but are entirely fabricated. It might cite a scientific study that doesn't exist or quote statistics that are made up. This is why these tools require human oversight, especially for high-stakes applications. You wouldn't want a medical diagnosis from ChatGPT without verification, just like you wouldn't want legal advice from it. The outputs need to be fact-checked and validated by humans with domain expertise. The models are getting better at this. RLHF helps them say, "I don't know," more often, but it remains a fundamental limitation of how they work. There's been an arms race in AI labs to build larger and larger models with the implicit assumption that more parameters always mean better performance. But the relationship isn't that simple. First, there are diminishing returns. Going from 10 billion to 100 billion parameters gives you significant improvements. Going from 100 billion to 1 trillion might give you smaller gains for exponentially more computational cost. Second, bigger models require more energy to train and run, raising raising both economic and environmental concerns. Third, smaller models that are carefully fine-tuned for specific tasks can often outperform larger general-purpose models in those domains. The future likely involves a mix: large general-purpose models for broad capabilities and smaller specialized models for specific applications where efficiency matters. The goal isn't just raw capability, it's useful capability per unit of cost and environmental impact. So where does this leave us? OpenAI's journey from GPT-1 to ChatGPT represents a remarkable achievement in artificial intelligence research, but it's important to see it as part of a larger story. These models didn't emerge in isolation. They built on decades of research in neural networks, natural language processing, and machine learning. They required enormous computational resources, the kind only well-funded organizations can afford, and they reflect both the possibilities and the limitations of current AI technology. ChatGPT has changed how millions of people work, learn, and create. It's accelerated research in fields from medicine to climate science. It's raised important questions about education, employment, misinformation, and the future of human-computer interaction. But it's also made mistakes, reflected biases from its training data, and occasionally produced harmful outputs despite safeguards. The technology is powerful, but imperfect, useful, but requiring careful deployment. Let's summarize what we've covered. OpenAI's progression from GPT-1 to ChatGPT represents a series of breakthroughs in scale, technique, and usability. The core technology relies on pre-training on massive text datasets, followed by fine-tuning and alignment with human feedback. These models excel at pattern recognition and generation, but lack true understanding in the human sense. They're most effective as tools that augment human capabilities rather than replace them. And bigger isn't always better. The right tool for the job depends on the specific application and constraints. The broader context: OpenAI's success didn't happen in a vacuum. They were building on research from Google, Facebook, and academic institutions. And they're not alone in this space. Companies like Anthropic, Google, Meta, and others are all advancing large language model technology. Which brings us to the next part of this story. If you want to understand the full landscape of how we got here, you need to understand Google's role, from the transformer architecture that made all of this possible, to their own models like BERT and Palm, to their response to ChatGPT. Thanks for watching. If you enjoyed this deep dive into OpenAI's journey, hit that like button and subscribe for more educational content on AI and technology.